Today's topic, we are looking at basement temporary works. So if we take a step back, what is it all about? It's essentially about making space below ground when it's not feasible to go upwards. There are other benefits such as increased security, because we're below ground. There's no ugly imposing views, so you can put a big multi-story car park with only limited structure above the ground, and so the neighbouring or the community doesn't get the hump with that development. There's also increased structure lateral stability, as the below ground structure can utilize the earth around it to take the lateral loading and also dampen vibration as well. It's quite a helpful benefit. But they are just a few. There's some real notable points regarding the type of temporary works required in basement excavation. The first being that it is incredibly varied and really dependent on the existing structure that you've got, which hence was why there's never just one solution fits all for these structures. There is generally a high level of risk. We're often adjacent to roads, other buildings, infrastructure, road and rail services. There's undermining other structures as well. So underpinning, do we need to put underpinning, or how are we going to ensure we don't undermine the adjacent structures? We're generally working in the ground where historically there is a lot of unknowns there. So that is a risk in itself. We have multiple disciplines all working together in a rather tight space. So we could have piling, steel work, underpinning, ground workers, and then we've got the temporary works and the permanent works all working together and the load transfer between them. That's quite a complex interface. We have multiple states of temporary stability, which is very sequence dependent. There's a potential for slope stability issues or global instability of retaining walls, making sure that the temporary propping removal at the end of the sequence is considered during the analysis of the new structure, because sometimes this could be a more onerous load case. Water can be an issue for sure. So the hydrostatic head pressure that you get from the retaining walls on the back of the retaining walls can be significant, and flotation of basement box structures due to the buoyancy and displacement of water is not to be underestimated. The retaining wall stability and global stability of the whole structure, not just the individual component design, is really important. To take a step back and look at the holistic view of what we're doing and how we're doing it and what are the effects of that on the perhaps multiple temporary work schemes that we've got there. And then finally, that the buildability is absolutely key. Clash detection and ensuring that the works as we expect them to go ahead can go ahead with the various propping or the various new construction that we're doing is really key. And that comes down to that engineering input and enabling that efficient construction methodology. And that's not engineering in terms of, well, you need to get some smart consultants on the job to start poking around and charging you massive fees. It's engineering in the case of we need to figure out and plan how we're actually going to do this and what's going to go where we're going to put, for example, the prelims, like the site accommodation. Where's that going to go? Does it need to move? It's all that planning, because when we're in a basement, it's really important because there's usually very little room even to swing a cat. So it's important to get that right. Okay, let's look at some typical examples. So I've put a few in here. We're going to look at the more domestic side first. There's got some photos here. You can see that these are domestic type properties where it's getting more and more common now, especially in cities where location is desirable but space is very limited. So they essentially build downwards in fancy car lifts and pools and things like that. But we've seen firsthand some of the effects that can become very apparent on structures if it's not done very well at all. If there's no engineering input, or you've got there's a thread in the shed kind of contractor just carrying out the work, then ground movement and can be a serious issue. So we've got a couple of examples here. The one on the left is a very good example. You can see that there's some ground support in there, so they're going down. They've got they've identified that because they're cutting a lot of structure out of the superstructure, they've braced it up. We've got the windows infilled with blocks and some wailers there. So it's all going tickety-boo, happy there. On the right-hand side, that is a job that we got called out to due to the complaints from neighbours, and the council came out to have a look at it and basically just said nope. So we came out as structural engineers for the council under a framework contract with another contractor. And you know when you walk onto site and there is a cement mixer precariously balanced on a single beam, you know that you're in for a surprise. So essentially what they started doing was just digging down without any ground support whatsoever. And this is a good example because this shows, well, what happens when you do that. The party wall in the center, or the dividing wall in the center, essentially is undermined. So the ground underneath it has no capacity because you've just excavated all the soil from one side of it, and it starts to drop. As that wall starts to drop, the surrounding building starts to drop with it, and you can see there's massive cracks opening out over lintels, cracks big enough to get your hand through, which generally from a structural engineer as advice, if you can get your hand into a crack that big, then you've got a serious structural issue. This is how things can go wrong, and they go wrong very quickly and are very, very expensive to remediate. Now on to some more commercial side of basement jobs. So you can see here, there's really got some large temporary works, massive propping in some instances, complex interfaces on boundaries that change on most elevations, and multiple disciplines all in one site. This is pretty complex stuff. So you can see we've got large excavators, raking props up to the walls. So generally what we're doing with the raking props or any kind of propping is we are replacing as close as we can the lateral support that a ground floor or a basement floor diaphragm slab is providing to that wall if we're going to be removing that ground floor or basement floor diaphragm slab. We need to therefore prop the top of the wall so we can take the slab out and then replace it with the permanent works, whatever's going in there. It might be a different floor level, it might be a different structure. And once the new structure is in and ready to take that load, then we can remove the propping, and we've got the new structure there and the open basement. That's generally the proposal. But the world keeps on turning during these jobs. So the loadings from traffic, infrastructure, such as trains, pedestrians, point loads from cranes for outriggers for loading out things. Those are the kind of things that need to be considered. So some typical constraints using this job as a example. So we've got surrounding roads. That means we've got a highways interface and a potential for a AIP submission to highways, which is an approval in principle. That can take some time to get through highways. So well worth planning ahead. We've got adjacent structures there, party wall awards and surveys, also things that take a bit of time planning. Underground structures, so there's potential for chambers, vaults, an underground road or rail tunnels, and then services as well. What services do we have nearby that will need to be disconnected? Or how are we going to affect them if we are digging a big hole next to them and potentially there's some ground movement there? Do we need to protect them or put in some sheet piles or some piled wall just to make sure that they're retained and nice and safe? So there's services which may be made of quite like materials such as cast iron, which are very brittle and don't like any movement. Well, very, very little movement anyway. So we really need to be careful if we've got known services around our site that are very sensitive, which don't like movement like that, because there will be some ground movement involved if we're removing a lot of the ground from inside of site. And then crane loadings. So a lot of material will need to be moved in and out of the basement, which is a number of meters down, often includes some craneage. High point loadings from plants such as this needs to be considered, and we need to figure out where that kind of strong point is going to be so we can design a basement propping scheme that's going to facilitate that. There are kind of the general constraints as an overview. I'm going to hand you on to Dave now, who's going to take us through some examples of typical retaining walls and propping solutions. So over to you, Dave.
All right, thank you very much. So yeah, I'm going to go through kind of the basics of what to be considering when producing a design brief and thinking about the design. And then both me and Josh have a couple of case studies to go through. So the main types of basement retaining wall, and these can broadly be split into kind of existing retaining walls and then new build. So on the existing side, there's a lot of masonry retaining walls and then reinforced concrete retaining walls. On the new build side, you're looking a lot of the time on sheet piles, reinforced concrete, or kind of contig or secant pile walls. So what we're looking to do is to maintain the support on an existing structure to make sure that we are not destabilizing it. So with a masonry wall, generally we need to understand how it spans at the moment. Is it spanning up and down between ground floor and basement, or is it spanning between piers? Are there kind of steel beams embedded within it? And is the facade staying it? Because generally masonry spans better left to right or across the way, but if there's a large facade still loading it, then your wall has a significant capacity to span vertically. Masonry walls often vary in thickness as well, so taking multiple cores down the height of the wall is important when you're specifying your site investigation to understand what's there. When it comes to the site investigation side, a lot of site investigation is undertaken within the basement of the structure. So the understanding of the ground around your retaining wall may not be there unless it's specified in the site investigation. A lot of masonry walls often have vaults behind them as well, which may or may not have been backfilled over time and bricked up, but that investigation needs to be undertaken. Concrete walls, generally a bit simpler, but it's also a bit harder to understand what's going on without doing the right SI. So which way does it span? It may not be obvious without kind of doing rebar scanning or breakouts and understanding what the foundation below ground is. With a masonry wall, it's generally just going to be built into the ground and propped by the basement slab. The concrete wall may be designed to cantilever. It may have a heel or a toe, and you need to understand that. And then on the new build, so a lot of the time that's easier to consider because you are designing the wall to align with your props, but you need to consider the temporary condition when designing your retaining wall. It's not, we've suddenly got this building here. How does that building get there? And has the temporary condition been considered when the new wall has been designed? So if we move on to the loading, so in general, your loading on a basement wall consists of a few things, and they're quite easy to quantify some of the time if you have the right information. So the main one, which is obvious, is your earth pressure, but you need the SI from outside your wall to understand that. It's important to consider water levels for basements, just to understand, especially with new builds or once you've demolished your structure, is there a case where uplift could be critical, or will it kind of fill with water up to ground level and therefore you have a much higher pore water pressure? As Josh has mentioned, if your basements are often along the edges of your site and there's a road outside of it, so surcharge loading, is there going to be any exceptional loads like cranes or other buildings that would kind of load your walls? And also, what is the level of other building foundations? Do they have basements themselves that kind of mean that there is no loading, or is their foundation at a higher level so that you get a significant surcharge halfway up your wall? When designing propping, it's important to consider what's going to be going on in site. Is an impact load going to be kind of credible, or how big an impact load is going to be credible during the works? So to summarize, these are the kind of things to be thinking about when you're kind of doing your concepts and thinking about your design brief. Is the current load path of the basement, can we, or we should always try to kind of replicate this to minimize changes in load path. consider is overturning or sliding critical, depending on the height of the wall and what loading you've got. What's your preference on types of props? So the main options are fabricated steel or proprietary, and it will generally be a financial decision which you choose there, and kind of procurement, the position of current structure and any proposed other structures that go around it, access requirements, ramps into basements, and kind of the temporary access around the structure, ground movement. A lot of this considers adjacent buildings and services, and if there's any kind of underground structures. So if you're in London, a lot of tunnels for the underground that you need to consider. If you're taking your basement slab out all the way to the wall to kind of put more piles in, do you do that in a hit and miss style? Can you get that out with your propping in, and can you get piles around your props? And then temporary foundations, can they be avoided? Because it's just a waste of concrete in the end if you can try to avoid them. And then can staging be used to simplify the scheme? So a lot of the times, I don't know if it feels like it's got worse to other engineers, but the staging of contracts now with the main contractor coming on and the demo contractor already having gone is how the contractual conditions of the project affect how the propping is designed. Does the demo contractor just leave a berm against the wall and let the main contractor do the propping, or is it part of the demo contractor's package? And does that then interface with the permanent works package, which isn't fully kind of designed at this point? So not really within our gift to control, but it's something to be considered when thinking about the overall scheme. So generally types of props, we've got a couple of examples which show a few of these, but flying shores, obviously they don't cause an uplift force onto your basement walls. I'm aware the picture on the right is not basement, but it gives you an idea of the kind of magnitude and the type of propping. It does resolve the lateral forces, but you obviously need an equal and opposite reaction on the other side to resolve the loads. Raking props. So these are obviously props that rake down to a thrust block or a permanent foundation or a slab. They will cause an uplift force on your wall, and that will need to be managed either through tying down to the basement slab or by mobilizing the weight of the wall through anchors. So that has its own implications. You will need some kind of foundation for these, be it thrust blocks or permanent foundations. So there's some examples there that show some fairly robust props onto some large thrust blocks. There's another example here which shows a different kind of propping, 2 levels of props. If Josh goes to the next screen, and shows the kind of how the propping solution would look in a slightly larger basement with a number of different levels to allow for the new permanent works to go in. And then there's some examples of proprietary and fabricated steel. So those showed a bit of both, but this just gives you another example. You've got a proprietary propping solution on the left there, or a fabricated steel on a new build structure, a big new sheet pile wall with a capping beam. So it gives some thought into what you are looking at. So I'm just going to go through an example of some sequencing now. So this is the project just showing the full process from you've got a basement full of rubble through to you've got your new build. So initially kind of demolishing that ground floor level slab, forming a berm of demolition arisings, which is where the demo generally stops. You've kind of taken out your existing structure and you've got your propping in place, or you've got your first level of propping in place. We could then remove that berm and we could then remove the basement slab. So the next slide shows that kind of process. You propped it at the top and in a hit and miss style would remove that basement slab while still maintaining support to the top of the wall. We've then installed further propping, which kind of supports the wall at mid-span with a new kind of basement slab formed at a lower level. The excavation then continues and further propping is installed to support it all the way down. At that point, you can then excavate to the base of your underpin and start to form your new wall. And You get your raft slab all the way in, prop in the bottom. You can then remove your lower levels of props in this situation, partly build your new liner wall against the retaining wall, but that will need some temporary propping to then enable the completion of the works, and you get your capping beam and your new ground floor slab in. And at that point, your basement propping is complete. So it's an example that kind of shows the whole process through from demo at ground floor level all the way down to new build up to ground floor. I believe Josh is going to run through one of his projects from a little while back.
Yeah, this is a great case study because it was a really refreshing project where the whole project team worked very well together to try and eliminate risk and drive that efficient design. It's the Landmark project in Manchester. It's a Bowman Kirkland project in Manchester Northwest, and I was the lead temporary works engineer for the project. And it's a really good case study because it had so many different interfaces that required lots of different solutions, because it was more like several jobs in one essentially. It was the winner of the ICE Constructability Award in the Northwest region for a number of reasons, really, which a number of them I'm going to cover today. So our involvement on the job were to design and plan the demolition works, which was for the existing 1920s theatre that turned into Odeon Cinema. And that partially demolished structure can be seen at the top left of the screen. The preliminary and the detailed design for the basement propping as well, we did that, and the new basement was deeper than the existing one, so that resulted in quite a complex solution being required there. We looked at the coordination and the sequencing of the removal of the temporary works to enable the completion of the new basement as well, and you can see the extents of that job on the right there. And the design of the various temporary works items as part of the superstructures being constructed, like anti-deck justification and some formwork propping, etc. But we carried out the work directly for Bowman Kirkland after having worked for the demolition contractor Foreshore Demolition. And because we were part of the project team quite early on during the demolition stage, that enabled the early involvement, really, which was key to making those good decisions early on and planning the construction of the new building, and how the temporary works and the permanent works could be cleverly designed to complement each other, really. The site location was on Oxford Road in Manchester city centre, and there was the central library up from the top left there, with Oxford Road railway station just down the road. I've also shown like an aerial shot here, which is the structure that was going to be demolished. It was an old theatre. A large auditorium in the centre underneath that bluish colour roof. And the site had some quite significant constraints, really, but mainly because it was in a city centre with some narrow roads around it, or a very busy road around it, and the infrastructure associated with that. The overall concept sequence of the proposed development was illustrated on some sketches to begin with, just to kind of communicate the idea of what was in our head and present to the client and to kind of sell the dream, if you like. At this point, the structure had been demolished and the basement had been backfilled in the majority of the areas to support the perimeter wall, and a high level pile mat was installed, and that was going to enable some of the contig piles to be constructed. And to save space there, we've because it was quite a tight area, we have utilised some geogrid reinforced walls to keep those batters on the berms like 45 degrees or steeper, which meant that there was less material required and less room taken up by that high level pile mat. The next general stage was to install the central raft slab in the middle and then use that as a base to prop off of to support the perimeter walls, similar to Dave's sequencing example earlier. That's really key to get something in there, and if it's permanent works, even better, because then you haven't got redundant thrust blocks. That construction of the central raft slab as well enabled the tower cranes to be installed, which would really start speeding up the project. Once the top level props were installed, then the lower level of the propping could be installed, which would permit the construction of some of the underpinning around the remainder of the slab, and we can see a scrap section there of what we deemed the section through to look like, supporting the outside wall, basically being a bit smart and using the new basement slab as a thrust block. So that's the general idea in a brief nutshell. Now we're going to go see some of those proposals in action. We can see here the berms to the perimeter walls, the high-level pile mats, and a 3D illustration of the propping there. But the prop installation was actually carried out in quite a balanced manner, starting from the middle of the raft slab working out, and that was just to make sure that we didn't get some kind of global movement on there, because we really wanted to avoid that. And the key challenges that we had to overcome turning that concept sketch into a detailed design was the coordination of the location of the props, for one, to make sure that we didn't clash with the permanent works, the sequence of that propping installation, the fabrication drawings, working with a structure which was very variable in terms of levels and out of plumbness, etc. So these issues were generally born out of trying to be as efficient as possible, which seems a bit odd really, but we did strive to reduce the amount of temporary works on site, and in doing so faced challenges, and these challenges are namely justification of the very variable structure in both form and construction, the design and the collaboration with other organisations such as the permanent works engineers, Curtains, who worked really well with us just to kind of try and streamline some of the construction processes and what the permanent works was generally going to look like. And that effort really paid off with reduced material usage and faster construction time as well. And it does take longer to justify the use of the existing structure as opposed to just bringing in some nice big props. And then similarly, it takes longer to prove the use of the permanent works in the temporary condition as opposed to designing some nice and easy redundant thrust blocks. But we like to work hard and challenge ourselves, and with this type of approach, it's really important to do that because we know that that collaborative effort really pays huge dividends on site in both time and money. So we can start seeing some of the propping going in here. There's generally 4 areas. Because we were propping the permanent works in most places, we had to have the propping designed and ready to enable those specific details to be incorporated into the permanent design, for example, on the raft slab where we're propping down to the raft slab. And having this system designed and ready well in advance meant that we could take advantage of all sorts of ideas to make that construction process a very slick process, so making the designs a slave to what you want to do as opposed to being a slave to your design. So let's take a look at some of the raking propping. We've got some of the raking props here, and the key component to this was that the soldier that was used to prop the outside of the wall, which is the vertical member there, this particular layout of the structure and the permanent works lent itself to having those vertical soldiers as opposed to horizontal wailers. But the key thing is that this soldier is a composite design. It's an anchored PFC channel to the wall at regular centres, and we're mobilising that perimeter masonry wall so that the wall is working as well as the steelwork channel. But why was this so important? So a more traditional approach would be a non-composite section would have been much deeper. That would have led to significantly thicker liner wall or piers at regular centres, both of which would compromise the internal floor area in the basement and require much more concrete, which we wanted to avoid. So we were working with the design well in advance, and therefore we could think, well, let's be a bit smarter about this. We could utilise the wall that's already there for some strength, and therefore reduce the amount of steel and reduce the kind of how much of the footprint that we're going to be taking up. And you can see here, this is the photo of the liner wall going in. That was near the core area. And you can see that the soldiers pinned back to the wall with the raking prop going up to the top there. In the corners of the structure, we had some flying shores, and these are horizontal shores, using that same channel beam, soldier channel being pinned up against the wall. All the props were positioned to minimise clashes with walls and columns in the permanent works, and that led to minimal openings in the new structure, which was great as each opening would need to be made good following prop removal, So we did a 3D model and clash detection process on there and moved those props to suit. On the north elevation of the basement area, there was a large extension, which was a contig pile wall with a capping beam at the top, and the contig piles were designed to span from the sandstone at the base to the capping beam at the top. So we just had to provide some of the lateral support to the top of the capping beam. And then once the new structure was in, the capping beam wasn't really required to do a great deal really to support laterally, as the new structure would be tied in to the diaphragm a little bit like this. So this capping beam was an item of temporary works in itself, really. In its short term during construction, it had to provide the support to the top of the contig pile walls and span between some point locations. But in the permanent case, it was going to be supported. You can see I put a photo there of what the car park looks like now. It's going to be supported in a couple of levels and not working anywhere near as hard as it was before. So the rebar and the side faces of the structure had to be increased to deal with that more onerous temporary load case. And seeing as we had a hand in some of that detailing, then we detailed some pockets in the capping beam just to make it nice and simple as we were installing it. In a similar vein, I'm going to show you what we did with the base brackets as well. So these were especially fabricated brackets that you can see here. And this essentially enabled the rebar detailing in the basement raft slab to accommodate some pockets and cast-in anchors. And the pockets reduced the load on the fixings, as the shear load that we would get, the horizontal shear load at the base here, was actually taken out by the direct bearing onto that back of that pocket. And that's a case in point really of risk reduction through design. That was enabled by getting involved early on. So the fixings in the brackets were also already in the slab, but they weren't doing they weren't working particularly hard in stopping the thing from sliding along the slab. So we weren't relying on workmanship on post reinstalled anchors to deal with the shear force. It was in a pocket, so it was going absolutely nowhere. And there's a GA of the setting out for those pockets there. As the new basement was deeper than the original, we had to underpin the perimeter, and this underpinning also served as a couple of purposes. It was both an underpin to support the wall above, but it was also a bottom strut to prevent the wall from kicking out, because we didn't have the benefit of having a large facade on top of the wall to provide that stabilizing force, holding that pin down. So we had to provide some form of support at the base. Traditionally, that would be some kind of steel prop, but if we had to put some blinding down there, then we can use the blinding to be that to do that job and remove some of the steelwork from the scheme. As the project progressed, you can see we were really glad that the hard work of the coordination of the propping paid off. It was quite close in some areas, but that meant that we didn't have to have some expensive patching up and making good with couplers, etc. Some areas we couldn't help the fact that we had some patches to make good afterwards. For example, when we're going through the B1 slab there, but we tried to put them in areas where you could use lapped reinforcement and make that solution a little bit simpler. So overall, the involvement of the project, or the project all working together to strive towards something which is efficient and very constructible. That enabled the demolition, the reduced level dig, basement construction, and finally the removal of the props, which ultimately led to the creation of Landmark in Manchester. And it was quite a complex project that had many interfaces on all sides, including the bottom where we were working with the sandstone. But we used as much of the existing structure as possible to provide an efficient solution in which the site team were really happy with. And we strove to keep to that mantra of ours of no temporary works is the best temporary works. And this whole process was made simpler and slicker and safer due to that early involvement and that planning well ahead. Led to reduced cost and improving program and some constructible and efficient solutions, which is really especially important on basements where a great deal of resources and time can certainly lead to some significant delays. Um, I'm going to pass on to Dave now, who's going to take you through a case study on Pilgrim Place. So over to you, Dave.
Yeah, so I have also picked a Beaumont and Kirkland project, which had some really good collaboration between the temporary and permanent works to get a basement in. So it's a bit of a theme coming on here. So Pilgrim Place is part of the kind of whole Pilgrim development in Newcastle, which has all been undertaken by Beaumont and Kirkland. It's been going on for, it feels like 5 or 6 years now. And we've been involved since Bank House, which is one of the early parts. That aerial view there shows Bank House, which is the tower block that went up, and you can actually see at the top the Carlisle House facade retention in place, which I've spoken about on previous webinars. The site we're talking about today is just next to Bank House. When they developed Bank House, they installed a contig wall along the west side of it with the idea that Pilgrim Place would be going ahead. But at that stage, 5 years ago, they didn't really know what they were building, but there would be a basement. So we were dealing with a new contig wall, but with no thought at that stage on what the construction of Pilgrim Place was going to be. So the capping beam on that wall hadn't been designed to take any propping and things like that. It was designed for the vertical loads only. So it's going to explain what led to the temporary works that we went for. And yeah, essentially, when we got involved, we were looking to get a 2-story basement in behind this wall and to provide temporary support to enable its construction. So another good example of early contractor involvement. So we got involved with Cundalls, who were doing the permanent works, and the initial thoughts were looking at knee braces, sacrificial thrust blocks with piled foundations. And we had a really good meeting with them and looked at, can we prop to the permanent foundations to reduce the amount of concrete, the amount of piles going in, and what we needed to enable that. And what we managed to do, because it was still early enough, was we moved some of the columns at basement level next to the wall to enable us to prop onto the permanent foundations. That was the major change that we managed that kind of helped the project proceed and kind of in an efficient way. There was also some downstand beams for kind of fire vents that we managed to move around a little bit to enable the propping to be more efficient. But essentially, we were looking at a series of raking props up to a whaler across the contig wall below the capping beam. And then in the corner where the amount of soil retained was slightly higher, we looked at knee braces to kind of reduce the amount of propping. So what you can see in that picture is one of the kind of developed designs where we managed to prop back to permanent piles. In the end, we managed to eliminate the sacrificial piles on prop 1 as well. So we only had 1 sacrificial pile cap on this project. And as you can see there, the loads were not insignificant when we started dealing with it. So what we came up to, shown on the next slide, was a series of props that generally followed the concept. We had 6 raking props with 1 of them onto a temporary pile cap, and then 3 knee braces in the top corner. And we designed these out of fabricated steel because that was the client's preference. Some of them we managed to kind of fit onto the permanent pile caps in like a bird's mouth thing, but due to clashes with the existing structure and to get it through kind of the fire vent holes to kind of eliminate patch up works, we used a kind of cast in plate detail down the pile cap. We also linked a few pile caps together with ground beams to distribute the loads and to kind of reduce the amount of, essentially to take those loads into the ground. So it was a fairly efficient solution in the end for the amount of load. There was a couple of interesting details that came up. There was, to avoid the clashes at B1 level, we, as I said, interfaced with the side of the pile caps and had a cast-in plate detail that was installed into them, and that made it for easy installation when it came to actually fixing the props on. The vertical loads, because a lot of these raking props were quite steep to line up with the permanent pile caps, we took those loads up into the capping beam, which was then tied back into the pile. So rather than trying to anchor our whaler along to all of the contig piles, what we looked at there was just strutting up to the capping beam, which in a lot of situations wasn't that far away, and then the loads being returned down the piles. There was also a tunnel in from Bank House, which had been designed 5-6 years ago where we knew there was a wall there, but it wasn't a kind of a wall that we could prop against. So we had to bridge over that, and you can kind of see that in that detail at the bottom. So I've got a few pictures of the general scheme. So you can see there that that was with all the raking props installed. The berm's still against the wall at that point, but yeah, a fairly kind of sizable wall to be retained. All the neighbouring buildings, luckily, were on piles, so there wasn't an issue with kind of surcharge loading from adjacent structures. There was a road on one side, but it was the loads from that weren't significant. And then you've got a further picture showing the knee braces in place with the whaler across the wall, and what was quite a nice pond forming at the bottom when I was on site. So yeah, in summary, a really good project for us. It was quite the solutions that we came up with in kind of collaboration with the permanent works guys and the piling contractor were fairly efficient for the size of basement being constructed, and kind of eliminated a lot of the temporary pile caps and a lot of what would have been wasted concrete in the grand scheme of things. So a good project. So yeah, I think that is a summary of how early contractor involvement is very important in basement schemes.
Thank you, Dave. A final section of today's kind of case study run throughs is just about site investigation, how that can drive some effective temporary works. This is a particular project where that was really important, because as we got involved early on, we were able to significantly de-risk the project once we kind of got onto site. This is a particular job had a underground canal next to it, which at tender stage we had very little information about, so we had to do a lot of guesswork. And at tender stage, it's very difficult because you can't really go in for just the absolute worst case, because you're never going to win the tender, essentially. So you've got to have an educated guess and do your research. We thought that this underground canal would have an arched roof from various archive data of underground canals in Manchester, of which there are very many. So we thought that if we're creating a basement next to the structure and we are removing the lid of the basement, then we're going to need to support the perimeter walls, okay? And from this particular part of the site, it wasn't really ground that we were holding up. It would have been the horizontal thrust of the arch, which we had to support. So that lends itself really to providing a number of raking props and a horizontal whaler. So it's 6 very large heavy-duty props at regular centres, and then a 12-metre long steel whaler beam. And that solution would have worked, but it would have really inhibited the site works, making room on an already very small site very, very tight. And it also relied on a very specific and controlled sequence of the installation of the permanent works, because we were propping down to the pile cap, a large core pile cap, which would have had to have been constructed in 2 stages. It's quite not impossible, but tricky to do, time consuming, expensive, etc. So that's the kind of system that we would be looking at, and you can see that's in plan here on the left hand side of that basement. It's quite narrow and short. However, once we got onto site, we were able to get in there and carry out a number of surveys. So several surveys, several site visits, and what seemed like endless hours watching endoscope videos. I was able to draw up that structure in 3D, and that enabled us really to understand the structure and therefore understand the loadings that were going to be acting upon the basement wall during the work. So you can see the structure here. What we found was that there's a former canal tunnel which was part of the Manchester Underground Canal network, but this particular area had been repurposed into a bomb shelter. And you can see the series of the concrete diaphragms there that were used as blast walls and concrete infill for the ceiling. And this meant that that horizontal thrust from the arch was actually going to be much, much smaller than previously expected, because the structure was actually relatively stable in this state, because the arches had concrete diaphragms underneath them. So the rationale behind the temporary works design was to utilise as much of that existing structure as possible to minimise propping and other structures that would become redundant once the new structure had been built. And that follows our, our efficiency motto of no temporary works is the best temporary works where we can get it. So here's the final solution. A series of diaphragms shown in orange there. Some of them are just bricked up doorways, and then a couple of others are some steel works, some steel bracing, quite heavy duty steel bracing. But what we essentially were trying to do was the horizontal thrust, or the part horizontal thrust from the arch. We were trying to just make sure that it had a load path down to the sandstone through any openings in the doorway, and using those orange diaphragms that I've shown there, D1 to D4, to assist in continuing that load path down to something that was solid. And these were the final solution. So we could see those steel frames in action. They were anchored to the walls and effectively enabled that transfer of loading from that structure to the sandstone. And because the temporary works was installed in this area, i.e. outside of the new basement, kind of in that access tunnel there, it was quite simple in terms of an interface between this and the propping. And generally, it was install the propping and the diaphragms, demolish the structure, construct the basement structure, and then simply remove the diaphragms. So that simple interface meant for a more traditional and faster construction methodology in that permanent works area too, as opposed to, what we had at the beginning was those large raking props coming into the site, which would have been really tricky. Okay. I think the projects that we've highlighted today really illustrate to me how important it is to get the correct methodology in the first place, which is absolutely critical for complex projects like basements. The right methodology changes from job to job and client to client, which is why good relationships between the project team and or those working on the project team lead to kind of good projects, and good in this case meaning safe, successful project delivered on time. That doesn't mean that you need to pay lots of expensive consultants fees. That's not what it's about. It's not what I'm trying to tell the group here. It's really just planning ahead, thinking about problem solving, how you're actually going to construct this and what are the issues that are going to raise up, and knowing about them early on to come up with some kind of solution to then therefore design something or come up with some kind of plan to overcome it, so that you're not coming across that problem when you're on site and you're in the mud in the basement and things are much more difficult. And that's it for today. So if you'd like to know a little bit more, there is lots of information out there. This presentation certainly isn't everything you need to know about basements. There's a lot of data out there. There's some good stuff on the Temporary Works forum, 5975, which I've put 2019 on there, but that's a bit naughty of me because it's 2024 now. It's been split up into two parts. So there's some good content in there. There's a couple of ICE publications that I've noted here, which is Temporary Works in Principles, the original one, that yellow one there, and also Part 2, which is a recent release, and various Syria guides. There's this iStructD Temporary Works Toolkit, which is that purple one. There's some good content in there. These essentially are helpful information which help you to de-risk a tricky basement project, and that enables you to make the right decisions at the right time. And after all, knowledge is power.